Hi guys, in today's video I would like to show you this RGB LED strip that I made. You can see it behind me, over there in the background. So let me interrupt this video for a moment. So let me explain why I've decided to make this project. I just basically wanted to prolong my day because during the winter the daylight time is getting shorter and I wanted to prolong my day. So I wanted to set up the sunrise from 6 a.m. and then the sunset ends at 9 p.m. and compared to current sunrise today, which was at 7:30, and the sunset was about 4 p.m., which is a quite short daytime. I've decided to create this RGB profile that looks like this, and this way I can wake up because of the light and prolong my day a little, like by several hours. So that's the reason why I've decided to make this project. So this LED strip is controlled via Wi-Fi. So I've used one of these STM boards and ESP8266 module with some electronics, and currently I'm running this application on one of my computers, and I have created this RGB profile, and I simulate the sunrise and the sunset, and currently it updates that RGB value every 5 seconds. And I've also made another application for this to control this RGB LED strip. I've created this Android application where you can set up the RGB value and click the set button, and it sends this command to the ESP8266 module, and then that message is sent over to STM board that sets the RGB value on this RGB LED strip. So since this application updates the RGB value every 5 seconds, in order to have full control with an Android application like this, I need to close that application because as you can see, every 5 seconds it is updated, and these two applications kind of compete, like which one of them will set that value. I can set it to any color I want, but since these two applications are running at the same time, I have something between 0 and 5 seconds until it gets updated. So that's basically it for the short introduction, and this is what it looks like. So I've placed that LED RGB strip at the top of the roll door, and it goes all over from the one side, from the one corner to the other, and all the way half down. And over there, there's my PCB. So as you can see, there are these MOSFET transistors and some bipolar NPN transistors, and this circuit is controlled via PWM at 1 kHz frequency. So therefore you won't see any flickering. So 1 kHz, I guess, is fast enough. And as you can see, here's that ESP8266 module, some STM board, and down here, here's the step-down module. And it is all powered via this cord, and it is powered by 12 volts. So before I connected all of this, I had to set this output of this step-down module to 5 volts, and I'm using this step-down module which has coil and switching component, because it's very efficient and it doesn't produce much heat. On the other hand, as you can see over here, I have a washer, and it is used as a cooler for this linear regulator, for this LDO. But linear regulators create some heat, which is proportional to the voltage drop across them and the current draining through them. So this one produces only some fraction of a watt, because on the one side there's 5 volts, on the output there's 3.3 volts for this ESP8266. So it's like 1.7 volts, and let me calculate it. It's 5 volts minus 3.3, so that's 1.7 volts. And the peak current of this ESP8266 module is about 300 milliamps. So let's multiply it by 0.3 amps. So that's about half watt of heat, of peak heat, but normally there's it consumes about 80 milliamps, so it is like 0.08. So it is well like 130 or 100 of something of heat. So it's not that much, but I've placed there a small washer to dissipate that heat. But on the other hand, these step-down modules that uses coil and the switching component, they are very efficient. So they don't need any extra cooler. And these MOSFETs can switch like several dozens of amps. So therefore, as they are switching just a few amps, they don't need any cooler either. So this is quite good solution. So that's all for the introduction, and in the next cut I'm gonna talk a little about schematics and this software. So let's continue with that. So now let's talk about the hardware first. So as you can see, the ESP module is connected via UART to this STM board, and then this STM board generates PWM, 3 channels which control these transistors that switch these RGB diodes. So the principle is quite obvious and simple, and the whole thing is powered by 12 volts. And as I mentioned, I've used this highly efficient step-down module that doesn't generate much heat, and this one linear regulator, this LDO, that powers this ESP module. Like this STM board has its own LDO on the bottom side, but it doesn't you cannot drain from there that much current. It's limited like up to 200 or 250 milliamps only, and this ESP module can drain up to like 300 milliamps on peaks. So that's why I decided to use a separate LDO, and I've connected this to the 5 volts because I didn't want it to produce that much heat, because when you connect it to the 12 volts, it will still work the same, but it will generate way much heat. based on the reasons that I mentioned a few minutes ago. So that's all about this hardware that I can mention. And also I can mention that this top frequency can be like several kilohertz, because these MOSFETs have quite high capacity between gate and source. So with this resistor it creates some sort of low pass filter. So that's why I decided to run this at 1 kilohertz, because it cannot handle like too high frequencies, and 1 kilohertz is quite smooth for your eye. You won't notice any flickering. But if you run this PWM frequency at about like several dozens of hertz, you could be able to notice some flickering. So that's basically it. And now let's talk about software. So let's start explaining this STM32 project. So first of all, I start these PWM channels that run at 1 kHz frequency and control the brightness of the LED RGB strip. Then I start this base with interrupt of the timer 3 that launches an interrupt every 20 milliseconds, and then I clear the buffer, enable the UART interrupt, and then I initialize this ESP8266 module. Then I enable this software watchdog flag that I will explain later. And here in this infinite loop, I just check the condition when the message handler flag is true, and then I call this message handler function. And this watchdog is also like a software variable only, but it helps me to detect whether or not this main thread is somewhere stuck or not, or when something gets stuck somewhere in the interrupt. So that's the purpose of this software-based watchdog. This is enable watchdog flag, and this is the watchdog variable that is zeroed over here. But when this main thread isn't launched, it means that somewhere else it is stuck, and this watchdog variable is incremented, and when the watchdog value is too high, it's gonna just reset the whole STM board. So this is just a simple software-based watchdog that can be enabled and disabled. But let's get back to the topic. Let's talk about this ESP server init function. So first of all, I reset the ESP8266, wait 2 seconds, and send a bunch of commands. And these two commands are interesting. This one starts a server that listens at port 80, which is a default port that web browsers uses when you try to access a web. They usually use this port 80 to send a request to a server, and this line tells the ESP8266 what's your login to your Wi-Fi router. So you just hard code here your Wi-Fi SSID and the password, and then it logs in. And this is the main function, message handler. So it is called from this place. So when this condition message handler flag is true, then the message handler is called. And this message handler flag is true when the stream of characters from the ESP8266 started and ended. So after the stream has ended, this message handler is called. So when you receive character by character, this timeout is set to 1, and it is set to 1 every time a character by character is received, and every character is saved to buffer one by one, and this buffer index is incremented. But once this stream of characters has ended, so the whole message was sent, this timeout variable is incremented, and when you basically wait more than 100 milliseconds, because this is launched every 20 milliseconds, and over 100 milliseconds this timeout is set to 0, so it means that this timeout will not increment anymore, and this message handler flag is set to 1. So once this jumps out of this function and this interrupt is cleared, then this message handler is launched, because this flag is set to true over here. And this message handler checks whether the get message from a web browser was received. So this string contains functions. It's gonna scan this buffer, and it's gonna check where this get string is contained, whether or not it is contained. So when it is not contained, the position and the output value of this function is -1. But when it contains, the position is some positive number, and then I basically send a response to the web browser and close the connection. So we can test it out. So we can call an IP address of your ESP8266 module in your local area network, and it has loaded this string, and that's basically it. But this get message is somewhere here in the buffer. So this is what an STM board actually receives. It receives 456 characters from this point to this point. So basically it contains plenty of information, like from where the connection, from where the request was sent, and what web browser you are using, etc. And I just ignore it. I don't care. I just need to know it was from a web browser, and I just send this string back. And when I receive this set LED RGB command, it is from an Android application or from the LED Strip scheduler. So it is from this application or from this one. So those two applications send this command set LED RGB, and I just check what's the position of this, because that received message also looks like this. So this is a command I've received, and I need to know the offset from the buffer, from the origin of the buffer. So once I figure that out, then based on that offset position, I can convert array to integer. So I will get these RGB values, and I will set the PWM according to that value. And then I close the connection. And afterwards I clear the buffer and enable the interrupt again. And sometimes it happened to me that this HAL UART receive function, because of this delay, it got stuck for some reason, but it happens very rarely. But when this interrupt got stuck, that's why I've created this simple watchdog variable with this counter, and when it gets stuck, this timer interrupt works, and it increments its value, and when it takes too long, the STM board resets. And when an interrupt is called, then basically it is somewhere frozen over here. So this watchdog variable cannot be set to 0 because this main thread, as it's supposed to run, it is interrupted, and any interrupt poses a main thread and does what it has to do in this interrupt function. But when it is stuck somewhere in this UART interrupt function, then this another interrupt function is capable of incrementing this watchdog variable, and also to reset this STM board. And you can place this reset to, let's say, to Hartfeld handler and in many places, and it's gonna solve a long-term running applications, because it is way harder to make a stable long-term running application, and you need to somehow you need to handle some problems that can come up with this. And the easiest solution is to reset the STM board or your application. So that's basically it for this project, and now we can move on to another application. So let's explain this LED strip scheduler desktop application in Java. So basically I just created a simple application with a simple stack pane layout, where I placed a line chart called light chart, and I've placed there several series for the RGB and the present series that represent this straight line and the current time. And I just generated just a few data points of the time. So let me show you that. So in this function initialize layout, I just initialize everything related to this line chart, and I've created this function to change the color of the series. So you just pass a line chart and also the color you want at position of the series you just load it. So therefore I can match the colors of these red, green and blue series, so they match with their name, because by default it generates some default colors, but I wanted to match these words with these colors. So this is a simple function for it. And over here I just also hard coded this data. So this is midnight, it should be black, so it's turned off. And this is a minute before midnight, and the RGB code is also 0, and this is the first data point at 6 AM, which is still black, but from this point to this point, which is 6:15, I just increment only the red color, and to 6:30 the red color reaches the maximum value, and the green color reaches only 64 value. So these are 8-bit values basically that I'm sending to that STM32 board, and during the day it is just saturated to full brightness at 9 AM, and since 19 or since 7 PM until 21 PM until 9 PM, it just lowers these red, green and blue values one by one. So this is how it looks like. You can create your own profile by changing these lines. You can add more of them as you want. And I also have a function that verifies whether or not my device is present. So I ping my smartphone, and if it is present, these RGB values are matching this chart. So, but when I leave the flat, these RGB values are set to 0. So when during the day I leave the flat, I just disconnect basically from the Wi-Fi because I'm outside, and then when several times it it cannot ping my phone because it's not online, it just turns off the LED. So the LED value will be 0, but currently it's 0 because it's night time. But when I leave the flat, it turns off those LEDs. So it's quite simple as that. And you can check the code, how I made it. The main loop is basically this timeline that also pings my phone and checks like whether or not my phone is absent. So when it is present, the absence is 0, and when I'm outside, the absence increments every 5 seconds, and after some time, if it is absent more than 24 times 5 seconds, then these RGB values are 0, as I mentioned. And otherwise, it's gonna calculate the RGB value based on that chart, and it's gonna send that RGB values to that ESP8266 server. So it's quite simple program, but you can explore it. I've created this class for the gradient list of the RGB, where I sort those data and can get those RGB values according to the current time. Because this timeline is launched every 5 seconds, but I need to get the current time in seconds and calculate like the current RGB value based on the time. So this x-axis is day in seconds, and on this y-axis is 8-bit value of the RGB. So that's basically it. So now we can move on to Android application, but before that I can show you where this application usually runs. So basically I usually run this JavaFX application on this computer. So when I approach it, it turns on the monitor, and when I walk away, the monitor is turned off. Simple as that. So I've used this computer also to debug my STM32 board in long run. So I just left this running, and I was just able to figure out when and why this STM32 board froze for a while, but because of some code issues. But this way you can find out like why your code freezes when you let it run in a long term, and then find out in what thread, in what function, on what line your code was stuck. But in this case I just wanted to check the message, but this way I was also finding out about bugs. So this Android application is quite simple. It contains only 3 SIG bars for the red, green and blue color, 1 text view and 1 button. And in this manifest file I just have these few permissions for the internet and the network state and Wi-Fi. And over here I simply just set on-click listener to this button send. So I just get this text view message that I convert to string and at end of line character, and it has this format that text of the text view, like set LED RGB. This is the command for the STM32 board, and these SIG bars basically change the values of that RGB. So I just set the maximum range of those SIG bars, and then I get the value, and based on that I format the string to have proper value, and then I basically format this text view message. So it's simple as that, and when I click that button, I just send data to server, and this function is the same as this Java function. So some parts of the code are the same, but this Java application is quite similar to this JavaFX application. So these applications at least share this function, and if you want to play with JavaFX application, you have plenty of tutorials online for these layouts, or also for charts. So it's up to you. It's available online, you can learn from it, and this project is also available on my GitHub, so you can read this README, and so you can check what I've made, what I've done. You can reverse engineer my code, whatever. Just learn from it, and see you next time. Bye.